Okay, good morning. Breadth versus depth. A lot of interesting ideas being discussed this morning. I'll do a little bit of breadth, but mostly go into depth. There's a lot of discussion around some of the ways that we've been integrating some of the latest technologies that we've been having the pleasure of working with our friends from Dassault. Basically, just a little bit about the bridge itself. It's just under 1 kilometer long. The main span is half a kilometer. Completion date 2021, not happening. Reason being, and I'll mention this towards the end, has to do with the contracting process that had many, many difficulties due to the nature of the way that contracts are done on public projects in Taiwan, dealing with quite complex information sets, such as this one. And what you have is this large bridge here, and the bridge is designed for car and vehicle access, but also for a light railway, roughly a tramway system that will be deployed in the middle of the bridge. So this is a span here between Danjiang and the Bali, which are basically on an estuary of the Tamsui River in the north of Taiwan. So how many people here have seen the movie called Margin Call? You know Margin Call? It's the one, if you haven't seen it, you have to watch it. It's about the 24 hours that basically caused the global financial crisis in 2008. Anyway, so Margin Call, there is a guy who's played by Stanley Tucci, who is one of the bankers who gets let go, and he says, in my previous life I was an engineer. And he tells a story of how he built a bridge in Ohio that allowed to connect people and saved, I don't know, an hour of travel time, and he calculated how many millions of kilometers of driving over those years had been. So this is exactly what this does. To get from Tansui to Bali, I think it's like, what, an hour or more? An hour and a half to drive all the way around to the other bridge and get there, and this now allows you to close that loop. So it's a very important piece of infrastructure, even from an economic point of view. So here's the dancer now dancing across the bridge, and the movement of these kind of cable stays and the arch is really about a dancer leaping, and it's something that again has to do with Taiwanese dance, has to do with a flow of movement, and if you like, a certain perceptual language of culture that we can basically map onto the structure here. And so how we express that structurally as well as architecturally became the challenge of the project. As I mentioned, also because of the views that it has. And okay, so this is what I wanted to show you. Here's the famous sunset. You see lots of people come here to see this very famous view. In Taiwan, it's a very famous thing. And they did not want the bridge to obstruct that, but if anything, begin to complement that. So this is something that before we talked about construction, before we talked about assemblage, anything like that, it was really all about how does this add value to the lives of people who are here and enhance, if you will, what they have. At the second point also, there was an issue of immediate constructability and explaining to the people in Taiwan how we were actually going to plan to build this so that in the end you could come up with a complete system that on one hand provides, there's that complement between the bridge and the mountain, and actually then there we go, now we can read this. So here we go. This was how this was arranged. So we have here a client body, which is the Ministry of Transport with their onboard engineers, Tuilin, very famous engineering company, led by, because it's an engineering project, had to be led by an engineering team. So the joint venture is between engineers, and as I mentioned, we played a very specific role that was not just the design, but was also then the whole 3D BIM integration process. So the idea was that we would have a design team that consisted of the three companies, Taiwan, Germany, and London, to provide a model. And this model, it'd be nice if this thing went forward. Oops, I think this died now. Ah, there we go. That we would then release it from our private workflow. This was sort of what we were proposing to the Ministry of Transport, saying we have a master model that we can share with you. And this eventually, when you provide a contractor, which they have finally done, and after many, many problems, which we'll explain to you why, that you would actually then have what we called a master model we can share, where then the contractor takes it on board and turns it into the execution model that is then released to subcontractors. So in order to get, I remember Boeing, right? We want to have authoritative data that we can manufacture from. In order to get the return on the investment that we are doing on building these kind of models, we want to be able to use it to the hilt, right? So this would then come out to fabricators, to concrete contractor, and so on. So we looked at what platforms are available that are fundamentally understood in engineering. And one of the things that was very important is that, for us, we have a set of skills and, shall we say, tradition of using the CATIA platform in Zaha Hadid Architects. It has its advantages. Other tools have other advantages. One of the things also that we found that was really fundamental is that, without really asking, Sinotech was using CATIA as well. And they were quite interested in looking at this kind of distributed collaboration. So the entire party here that you're looking at would not have happened if you'd not had two parties on either side, Zaha and Sinotech, that were not willing to work together on a common platform basis. If you don't have that, you might as well not even get started, because it's just going to become a major headache. So we talked to Dassault, we talked to, well, to Jeff and to Patrick on our side. They then talked to your counterparts in Taiwan and looked at what is the infrastructure required. If you remember the work that's been done in PLM and DMU, in the airline industry, how do we integrate that across architecture and construction? Don't forget that this is really an engineering project, right? So basically there's a series, shameless plug here because we are talking about 3DX today, but there is basically a platform for engineering and civil engineering that became one of the mainstays for designing this together. And one of the things that's interesting about this tool, the way that it's developed, this is a far cry from when I started using CATIA back in 1998, but basically is that it now is first and foremost a platform for collaboration. And this was something that was very important to us. Remember what I said before about the Galaxy Soho project, about how do you collaborate across cultures? How do you collaborate across mentalities, ways of work? Having a common basis for which we can share information and track who's changed what and who's issued what became very, very important. So this idea then that all the information is stored unequivocally in the cloud. We don't have this with Revit yet. This happens here by the very nature of the way that the tools are built. All the information must be not even file-based, but it's actually object-based, and it's stored on a common platform, means that anybody who can tap into that platform, in this case our local partners and then the contractors in Taiwan, has access to the information. So similarly to what I explained before about the say the airport in Beijing, again we have a series of logical assemblies. We have the tower, which is the main mast. We have the deck, so this is concrete, this is steel. We have all the barriers and furniture that we have in there. We have then lampposts, cables, girders, and so on. So this becomes the basic assembly that allows us to systematically and hierarchically build a bridge, right? Because this is a true engineering project, we're not dealing with things that we're dealing, say, on the airports right now, fire safety, evacuation, egress, coordination with baggage system. I think a lot of people from the Navi team are sitting in the audience today and are all nodding wearily. Here we have really a very logical assembly of components that each speaks to and represent a particular trade, a particular subcontract, either steel, concrete, or otherwise, that enables the bridge to be built. So this is a logical view of the assembly. So if you put this all on the 3DX platform, it has this funny, I'm sorry, it is kind of funny, Lazy Susan. If you go and eat dim sum in Chinatown, do you know these, right? I'll have a bit of, you know, egg rolls and a bit of whatever, and this thing flips around and you got the stuff. It's kind of funny, right? So what did we put in the model? So we put basically the whole of Taiwan, or most of Taiwan is in the model, just to give us at least the north of Taiwan. We have the city of Taipei here. We have here the Danjiang Bridge at the estuary of the Tamsui River. And just for comparison, here we have the Taoyuan Jichang, which is the airport in Taoyuan. This is where Richard Rogers is building the new Terminal 3. And the city of Taipei in between those. So this gives a sense of scale, and then having an immediate and site resolution, which then allows us to place the bridge, including both bridge heads, and do the engineering for that, including foundations. So the entire bridge is modeled on this platform. You'll see the level of detail we get to here. There's no other software that I know of that can do this, because of the way that it manages memory, and the way that it moves between, again, it's a whole other lecture, between a virtual representation mode and the way that it actually calls up shall we say, the actual modeling modes. The ways that it manages memories and representation is pretty unique. So it combines, say, what Revit and Navis do in different platforms, it does it in one. That means you can switch very quickly between working on a model, coordinating it or visualizing it without having to download all the stuff that goes with it. So here's an evolution of the bridge mast. This was the most important part. Remember this idea of the dancer having a certain lightness to it, a certain fluidity. There's also a certain panache here that we were interested in, the slight bulging of the mast here. This is something that Zaha was very interested in at the time. Also this kind of shifting from convex to concave geometries in concrete, but everything that we do must be built with the same economy of scale, with the same budget, the same per square meter rate that we would do if we built a simple stick. That's the only way that we can justify doing this. So if we start with the mast is engineered really after having gone through the basic competition design, is taken down to a very simple set of functional guide curves that define the exterior profile and then the step profile of the mast. The mast is symmetrical in itself. And then start looking at the segmentation. In this case, there are 4-meter segments that will then be used for what will eventually be what you want to do, which is a slip-form concrete casting system. Now, if you go around London, you see they're building lots of towers, you'll see slip forms going up, and they're building the same core, it's the same slip form going up, 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 and it doesn't change. Here, it's continuously changing. That normally means you would have to build a mold for each one of these segments. It gets more difficult because as we started doing analysis on this, we find that even if rationalize this, there's a dirty word that gets abused today. If we start looking at its constructability and say, well, what it's really about, it's not so much about the concrete, it's really about the geometry of formwork. So if I can control the formwork, I can control the geometry. In this case, we're looking at various incidences in the original design. If we had more time, we'd go through this on other projects like Galaxy. But basically, if you have the general case of different segments on the base of the footings, where you have a convex section, and then it switches, you see, from the convex to the concave, that transition incurs a shift in Gaussian curvature, right? So this means that we are no longer dealing here with any kind of developable planar surface, but actually we have to look at how do we simplify the geometry so that we can build it within a certain cost framework. Because we have this curvature shift. If you know the mathematics, it's basically differential geometry, 1 over the square root of the largest and smallest curvature radii. That will give you a certain number that will tell you if this can be met by a particular material elasticity. So that has to do with, are we going to make these formworks out of phenolic? Are we going to make them out of wood? Are we going to make them out of steel, which drives the cost way up? And the client says, well, I just want a slip form. I don't want all this funny stuff. If you want to do it, find me a way to do it. So we went through all this series of improvements to see how we can actually get as much of a continuous developable nature to the surfaces so that they could be built with single curved surfaces like a phenolic board. And then what became really important is really the geometry that defines the section. And this is the one that varies going from the base to the top. Now what's really interesting here is that this is tied to structural performance. So we can't just model this and say this is going to be nice. LAP, who did all the structural engineering calcs to this, basically they worked with, I don't know, I think one of the smartest people I've ever met, which is this crazy guy in Argentina. And his name was, I can't remember, Manuel Miguel, what it was. And this guy only works in AutoCAD, and he writes this he's a structural engineer, and he writes this crazy C++ code that calculates sections and outputs it from AutoCAD into drawings and into an Excel spreadsheet that interfaces basically with Sophistic. Sophistic is the structural engineering tool used by LAP. Brings it into AutoCAD, does the mathematical calculations for the sections, outputs them, and then we had to reference his sections into our design to check that actually we would implement the structural engineering requirements so this thing actually would perform as required. So this is really, really important, this step, because it's about marrying a structural engineering performance with an aesthetic design intent. We did not want, if you just left it up to them, they would have just drawn a simple stick, or there's other cable stay bridges We saw one earlier, which are kind of geometrically a bit simpler. Here, we really wanted to maintain kind of the fluidity of the geometry. And I think the important thing here is how are we able to verify that back to Taiwan, saying this actually implements the structural requirement that is going to make this a seismically safe bridge. So the platform acts as, you know, we're talking about the platform here, so I'll mention that, but basically it acts as also as a very powerful review tool, so again, that we can mark up, continuously submit comments back and forth between ourselves and our partners. The important thing that happened here, or the breakthrough I think that allowed this project to happen, was a collaboration we had with Perry. Perry, as you may know, is possibly the most advanced formwork fabricator that you have on the planet. And this is Mr. Brunner here in their facility near Augsburg in the south of Germany. Very well worth a visit. And what Mr. Brunner has, he's like basically their evil genius, is he developed a variable geometry formwork. So basically, you can use this on slip forms, and you can slip up the side of a building, in this case our tower, and this thing is basically being controlled with these strand jacks, which are digitally controlled, and as it moves up, it does this, and it changes from a convex to a concave with a standard slip form construction method. This was the most important thing to demonstrate to our clients that there was a possibility of building this tower without having to create a single bespoke mold for each segment, but rather being able to build it with one adaptable system. So the proof is in the pudding here, is in the variable geometry formwork that we were able to put forward in such a way that the client made it a requirement for the contractor to demonstrate that they were able to do this, because of course that fulfills the design intent. So if we start going up the building, this is now some shots of the model. I'll mention that what's happening with the construction in conclusion. And you see what's happening here. This is the structural steel plates. I'll talk about those in a minute. These are dampers that connects the two fairways of the bridge where the cars and the railway ride on into these stabilizer beams that then have these dampers that basically take up any movement of the bridge, so that if you're driving across, it's not all wobbly and weird. And you can see what's happening here. So the model that we designed, we built all that logic that you saw of the formwork in collaboration with Perry into our own completed concrete model. These are the ties drilled in. Remember, these are true solids, right? This is not representation. This is a one-to-one virtual twin. You can measure the volume of concrete here. You can measure the pockets of concrete that we're removing concrete. And most importantly, all the rebar here, this is now done by our engineering partner in Taiwan, by Sinotech. Each one of these, every single piece of rebar is modeled in this model. And that means that because these are true solids, I can actually select all this rebar, measure its volume, multiply it by the density of steel, and I know exactly how much steel I'm using, or linear length of rebar, or whatever. Now this is required because it's an engineering project in Taiwan. Remember, this is under the engineering directorate. We have to demonstrate every single piece of rebar before we get the go-ahead to be allowed to do this. So to have this level of information in the entire project, I don't think there's any other tool that could have done this, where you can just open it still, flip it around, cut it, section it as ever you want to. This is the reason why we went down this path. Okay, as you can see here, these are the cages, the rebar cages with the rebar ties. You see inside here then we have large tension rods that are cast within to provide pre-tensioning of these towers. I see Rob May nodding. He's like, we can go through the structural engineering stuff. So this goes right down to the ties of the rebar, right? And you can open this model and you can zoom in and out, and the system will allow you to do that and load and offload whatever it's not showing. But we needed to have this level of definition, and I'll explain to you why. Because you need to show every single one of these rebars in a drawing when you're going to tender. So if we're going to draw all of this, and that's where the pudding, proof is in the pudding comes later, it gets quite a lot of documentation. So again, here we have the X side of the bridge, the tower. You see here, I'll talk about these in a minute, these are the cable stays, these are the sleeves cast in. In the middle of the tower, we have a giant steel box that goes up and provides the main stability for the tower. It's like a giant concrete core, steel core. So think of it as one giant SRC, steel reinforced column, to which then the cables stays are actually tied. The same holds true for the pylons. So this is then the concrete pylons underneath the bridge. So when you're reaching the bridge itself, again, same calculation of the formwork, analysis of which parts can be simplified into flatter developable sheets. Where do we have double curvature, which was important, element of the design to be maintained. So this is then, again, our geometry designed in-house, which is then passed over through the virtual collaboration platform to the Taiwanese team, who then start providing all the detailing. Right, you see the rebar starting to come in, and then again 2 hollow core sections here in the pylons. All the work of the modeling that you see here on our side of Zaha Hadid Architects was done by 4 people. The core team was 3 with an augmentation of 4. That's all we needed to do the entire project. And so that's very efficient, right? If you look at how you spend your fees and your profitability, that's a very good way of doing it. Again, same thing here. Here's a full rebar complement. You see here, again, these are pre-tensioning ties cast into the concrete. Again, this is the basic roadway design. Again, remember that we have traffic requirements here so that we have safe traffic movements of cars. These curves are very special curves. They're called clothoid curves. I don't know if anybody of you knows, but it's basically a curve that very smoothly transitioned from zero curvature and begins to adapt the curve. Would you like to add something to that? And what happens is we then have a series of adaptable sections. In this case, it's a section of the entire steel profile of the bridge that has a series of constraints built into this that make sure we always have the drainage implement, we always have the right dimensions implemented, and this then adapts as we move it along and cast it in each location of each segment of the roadway. So you see there's a lot of detail in this model. All of this was added to it. If you then look at inside, these are then those sections now really done as shipping technology. These are steel plates, which then have access hatches already built in. These are then pre-assembled and prefabricated and brought to the site by barge and lifted into place. We have this other end now, the cable stays. The cable stays here are now welded here within to providing, if you like, the other end of the tension of the bridge. So this is what I wanted to show. These are other LAP bridges that shows you roughly what's involved. So this is a cable stay. You see what happens. The roadway is built in sections, brought along by barge and lifted into place. And when they lift it into place, they then attach the cable stays. And they do it. It's really interesting. We went to see this. They were finishing a bridge in Scotland. And they have to do it side by side. So, right? So you see this is a problem, right? This is standard cable stay tower. And this is, you can see the slip form segments. Remember, ours instead are changing in geometry as we go up, like so. Okay. So one of the things that we modeled, for example, that was really quite impressive, I thought, that the team did, you have not just all the cable stays, but to remember that the cable stays have a sag. So the actual cable stays are not straight, but you see that they deviate into a curve. And that curve coefficient is something that we modeled because it allowed us to have the right. So you see there's a sag here, there's a delta. And this sag is very, very precise because it's actually not a straight line, but actually has this sag that takes up slack in the movement of the bridge. So it's that level of precision of modeling. This is coming through what's called a design table. A design table is basically a connection between Excel information that, again, is coming from the engineering team back straight into the modeling and modeling this so that they're actually accurate. So again, by having these accurately modeled ties, it means that the contractor can very accurately estimate what is the information and the quantities required to get this built. Right? So here we're looking, in this case, I think it's, if I'm not mistaken, it's a sag table where we're looking at where is it acceptable, where is it moving kind of beyond. Here you see, again, an existing bridge. You have the cable ties cast into the bridge, and then, if you remember, tied back to the steel box in the back. And so this angle for each one is changing. Again, with the design table, we're able to infer and generate automatically every single one of these cable ties. So if we go down into the bridge, there's a lot of stuff, right? You see there's bicycle racks, there's wind barriers, there's furniture. And because we wanted this to be a complete project, basically we actually modeled every single bit. So we have here railings. This was done again all through constrained geometry development. We designed a nice bench that is made of a curved steel plate with wood on it for people to come and sit down and see the sunset. We even designed the bike rack because we're crazy. And so we designed our own bike rack. And then these are, again, additional balustrades for safety. Wind barriers that deflect the wind. It gets very windy there, so you don't get blown away while you're walking across. All of this is in one model, yeah? And finally, these are also acoustic barriers. So these are big acoustic walls. That means that when you're standing there, you're not kind of blown away by all the noise. So this leads me to the final bit, which is, because this is a public project in Taiwan, we advocated very strongly that you should take the model, all the information is there, down to every nuts and bolt, and basically execute directly from the model. And unfortunately, they said, no, in Taiwan, we have to submit drawings. So we produced all the drawings directly from the model. These became the basis of these became the architectural drawings, again, coming from the live model, so as was previously mentioned, any modification we make, updates here. But they then became the basis for the engineering details. So all that rebar that you saw still had to be put onto 2D paper, even though nobody will ever look at it again. So you see here, this is a plan view on different A0 drawings because this thing is so big. All the geometry for these bent light posts. So this is what I want to conclude with. One of the reasons this project is delayed, was delayed, is because they had to go out to tender 6 times, and they all failed. And I think on the 7th try, we were able to get a tender. So that took almost a year and a half. Now, why did it fail? Because all the contractors in Taiwan did not agree, because they all know each other, on the budget being proposed. And as a result, they all got together for dinner and say, none of us are going to bid. And you needed at least 3 contractors to bid, or the tender would be declared invalid because you did not have enough vendors. This went on 6 times. As they got to multiple times, the requirements were reduced, and finally a contractor emerged. Each time, the government upped the ante with the budget, and finally we had a contractor. So the government said, this is how we are going to build this building, like this. So here is LAP and Sinotech and Zaha. We are managing all the 3D data. Some of this, Sinotech and Zaha were working off the Dassault 3DX platform. LAP chose not to because they were really only working on the pure mathematics of this. So that was interfaced via Sophistic and Rhino to those CAD drawings that you saw. But each one then had to put out their own CAD drawings, which Sinotech completed, and the entire project is almost 1,500 drawings. When you chop up that model, you get 1,500 drawings, and that is, by law, on a public project in Taiwan, the instrument of contract. That goes then to the contractor, who then generates their shop drawing, but the government said, we need you to run it off a 3D model. So they said, we want you to take this stuff and build your own 3D model. And as you all know, the chances of this 3D model and that 3D model looking the same are 0, right? So that is a problem. And also the amount of wastage, every time there's a query, you know, has to go, it's like insane. So the first thing we said is, and this took many, many workshops with the government, is where we have CATIA version 6 or 3DX, whatever you want to call it, has no authority. Remember the authoritative data from Boeing? Can we adapt? This is something that we did for many years when I was at Gary's office, where you actually have a legal framework, a legal qualifier that takes data which is not enshrined in a standard contract, because the contract only talks about drawings. You can't stamp a model. You know, Gary's, we used to sometimes stamp a CD-ROM or a DVD-ROM, or, you know, do you stamp the computer? I mean, it's kind of difficult, because contracts and drawings go back over 100 years, right? So none of the people within the government, the civil servants, wanted to take that risk of saying, I will allow you to change the practice. So we said, if we provide a qualifier, could you at least elevate the 3D model so that it is parenthetic in the tender process, not just to the drawings, but where the drawings, this is what we did in Galaxy Soho, this is what we did at Gary's for many years, is now standard practice, but this goes back a ways, where basically you can work equally off the 3D data as well as the drawings. Even though this remains the instrument of contract, you're actually effectively working directly off the 3D data. And ultimately, if there's agreement, use another qualifier where that model is taken directly into the contractor's modeling environment. You bypass all this stuff, don't chop down as many trees, and basically you take the geometry straight through. Now, the process of getting this accepted in a government body in Taiwan has taken about 2 years, and we're still not quite there yet. The reason we're getting there is that the contractor says, of course, it makes total sense, because instead of having 20 guys rebuilding models off of millions of drawings and constantly checking back, I'll just take this, we'll verify it, we'll save lots of time, and off we go. So it is an issue. It goes back to, remember, the human component of how do you massage and control a process like that, where technologically it's there, it's just that the legal framework isn't there. So in conclusion, while we wait for the bridge to happen, we're now just waiting for groundbreaking. We're waiting for the president of Taiwan to come to the groundbreaking ceremony, which has been moved twice because she's very busy, but hopefully that will happen, I think, on the 14th of March now. Will happen next week, the groundbreaking. Until then, we have, they're looking at souvenirs. You can buy the bridge like this. You can have a beer coaster. You can have a shopping bag, a tote bag, and, wait for the bridge to come. Anyway, thank you.